Welcome to the PractGate YouTube channel. So today we'll be learning about the stability of structures, and in that we'll be covering the overall stability of structures. What is overall stability? What are statically determinate structures and what are statically indeterminate structures, and how to find static indeterminacy. So first let's begin with overall stability. Okay, so what is this overall stability? Overall stability consists of external stability and internal stability. So in external stability, we take this example. You have a 2D structure and a 3D structure as well. So in 2D, we have this, let's consider it like you are holding a paper over there. If you want the paper to be stable, what would you want? You wouldn't want it to move and you wouldn't want it to rotate. So you wouldn't want it to move or rotate. Yeah. So for that, what do we need? We need the summation of forces in x direction to be 0, the summation of forces in y direction to be 0, and the moment in z direction, moment about the z axis to be 0. So that's why what we have here is you have these three equations of equilibrium. In 3D, you wouldn't want your object to move in x direction, as in x direction you wouldn't want it to move. You wouldn't want it to move in y direction or in z direction, and similarly you wouldn't want it to rotate in about any of the other axes like z axis, x axis and y axis. So you wouldn't want any rotation over here. So this is why if you go to count the equations of static equilibrium, these are called the equations of static equilibrium. So in case of 2D, you have this 1, 2 and 3. So in 2D we have 3 equations of static equilibrium, and in case of 3D we have with respect to displacement 1, 2, 3, and with respect to rotation 4, 5 and 6. So we have 6 equilibrium static equilibrium equations in case of 3D structures. Okay, so then we come to internal stability. So what does internal stability mean? Now consider this a beam and these two are the hinges, and you put a third hinge over here in the middle. So what will happen is if you place a vertical load, you put any load on it, there will be a deformation. But how will it deform? It will deform rigidly like this. This pin will come down here. So this you wouldn't want it. Elastic deformations such as this are allowed, but this is called as rigid body movement. This is not allowed. So now we come to what is the minimum number of members which are required to maintain this internal stability or geometric stability also. It's also called geometric stability. Okay. So for that, let us start with a 2D example. So what we have here is, consider this as a square truss, you can call it. Now what we do is, let's just try giving a push on this side, on this pin. So what do you think will happen? So what will happen is that it will just fall like a pack of cards, you can say. Like you just push a card like that, it will just fall like this. Okay, So what will we call this type of structure? It will be unstable. So to correct this, what will we have to do is we'll have to put an additional member, diagonal member like this. Now what is going to happen by putting this member? So what will happen is, for this structure to fail, first this force will have to compress this member, which will be difficult. Okay, why? Because this member will give some resistance to that. So that's why it will help in maintaining, to keep the structure stable. So what you see over here is two triangles. Okay, so these two triangles are formed. So why is that? Is because a triangle is considered uh, as the strongest shape to support loads. Okay, so if you apply this same push on this, it will be stable. The structure will be stable. It won't fail so easily. Okay, so when we go to count the members, let's just take an example. Now suppose if we want to add another joint, so we add this joint over here. Now to connect this joint with the truss, you connect it with this joint, suppose. So this becomes one member, but still it will be sort of just hanging in the air. So you get another member. Okay, so for every joint you require two members, one and two. So that's why what the equation will be is the minimum number of members to maintain geometric stability. So two members per joint, so 2j minus, now you see here you have the extra number of members. So how many extra members you have? 1, 2 and 3. So you subtract 3 from there. Similarly, when you come to a 3D truss, you have like this. Consider this as your joint, as your extra joint. So to connect this one joint, you require 3 members, 1, 2 and 3. Okay, so that's why what happens with that is you have minimum number of members 3j minus, already how many members you have is this one, sorry, this 1, 2, 3, 4, 5 and 6, okay, which have already been used up. So you have 3j minus 6. Okay, so next let's move on to see what are statically determinate and statically indeterminate members. So statically determinate. So by the name itself, you can tell uh, determinate means obviously to determine, to analyze, to calculate, you can say. So uh, what do we use to determine? So what do we determine is the forces. So to determine them, you use the equations of equilibrium, which we discussed earlier on top, equations of static equilibrium. Okay, so equations of static equilibrium. So using them, we determine whether a structure is statically determinate or whether it is statically indeterminate. So if the structure is being, you can find the forces or the reactions in the structure just by using the equations of equilibrium, then it is a statically determinate structure. But if they are falling short, as in you have more number of unknowns than your equations of equilibrium, then it becomes a statically indeterminate structure. Now, what they say is statically indeterminate structure also has its sort of pros. When is it helpful? Sometimes it is helpful when, in case there is a sudden loading. In case a member fails, then these extra members or these extra unknowns, you can say, they help to support the structure. So in that case, the structure is stable. But also the cons is that you can't estimate properly that what is the nature, how much it can handle or anything. You can't determine the unknown forces because you have little resources to do so. Okay, so that's basically the difference between statically determinate and statically indeterminate members. How to determine what is the static indeterminacy? Now, this is a question which is asked in a lot of interviews and things like that. So for that, the overall stability over here, your degree of static indeterminacy is equal to degree of static indeterminacy is equal to external static indeterminacy and internal static indeterminacy. So for the external part, let's just say you consider this. This is a fixed beam. You can see fixed supports on both of the sides. So in case you have a loading like this, you have an inclined load. That time, what will be the reactions? Of course, you know, for a fixed support, you have three reactions, one vertical, one horizontal, and one moment. Okay, same thing goes for this side also. So why you have this horizontal reactions here is because of the components of this force. Now, this is the resultant force. If you divided it into components, you will get this horizontal component and this vertical component. So according to that, the reactions will be developed on both sides. Okay. So for this specific structure, now if you go to find the degree of external static indeterminacy, so DSE will be equal to first the total number of unknowns. Okay, so we have one, one, two, three. Okay, so three here and three here. Okay, one, two, three. So 3 plus 3, you have 6 in total, and you have, since it is a 2D structure, you have three equations of equilibrium. So for this, the degree of external static indeterminacy is 3. Okay, so for this it will be 3. But consider this situation. If you have vertical load like this, that time what will be the reactions which will develop? Now you can see that there is no horizontal component for the load. That's why there won't be any horizontal reaction which will develop. So you will only have vertical reactions on both sides and the moment. Okay. So now if you go to calculate the external static indeterminacy, you have total number of unknowns 1 and 2, 2 on this side and 2 on this side, which makes it 4, and you deduct the equations of static equilibrium for a 2D structure. So there we have 3. So for this it will be 1. So your external static indeterminacy for this, for just a vertical loading on a fixed beam will be 1. Okay, so that's how you find your external static indeterminacy. Now when it comes to internal static indeterminacy, you have two conditions. One is for a truss and one is for frames. Now even in trusses we have a 2D truss and a 3D truss. So let's see according to that. Now what we know about trusses is that trusses only carry axial load, right? So they just carry axial load. And where is it carried? It's carried on the hinges. Okay. So your degree of static indeterminacy given by dSi is equal to, first of all, the total number of internal reactions, and you remove the available equations of equilibrium. Okay. So first, to find the available equations of equilibrium, what we know is that for each joint in a 2D truss, it will have summation fx equal to 0 and summation fy equal to 0. Okay, so you have these two equilibrium equations over there. This is for each joint. So from there, what we get is 2j, and if you go to subtract the available equations of static equilibrium, because you already have those three, you remove them from here. Okay, so this becomes your available equations which you have left, and the total number of internal reactions is equal to the total number of members which are there. So that's why for a 2D truss you have the equation as dSi, which is your degree of internal static indeterminacy, is equal to the number of joints minus 2j minus 3. Okay. Similarly, when you come for 3D, now this is for 2D, when you come for 3D structures, that time your dSi will be equal to m minus. Now in place of 2, it will have three equations, which are f summation of forces in x, summation of forces in y, and summation of forces in z direction equal to 0. So that's why you will have it as 3j minus, and you have 6 equations of equilibrium in 3D structures, so it will be minus 6. So this is in case of 3D structures. Okay, so this we were talking about trusses. Now when it comes to frames, there is one thing in frames that this equation, as in static indeterminacy, is there only in closed loop frames. Okay, closed loop. Okay, open loop frames will be determinate. So since we are trying to find static indeterminacy, that's why it will only come in closed loop. So let's just go further down. Okay, so here we are talking about frames. Okay, so there is this equation, uh, internal static indeterminacy in case of frames. We have it as 3c minus r. Okay, so it used to be like this. So what does this mean? Now it is assuming that your frame is rigid, as in it has all rigid joints. Then this RR, which is number of internal reactions released, released will be 0. Okay, this is in case of rigid frames. Okay, or rigid joints. If some of the joints are pin or hinged, then this won't be equal to 0. This RR will be there. Okay, and this we are talking about in 2D, so that's why it is 3C. Okay, because why this 3 comes in places, because every member will have 3 forces internally. So what are those? You have Fx, Fy, and moment. Okay, whereas in a 3D structure there is Fx, Fy, Fz, moment about x, say, and moment about z. Okay, so this is in one loop. So this is the number of closed loops. Okay, so that's how we get it for a 2D structure. Now if it was 3D, the equation would be internal static indeterminacy in case of a 3D frame 6C, since 1, 2, 3, 4, 5 and 6. Sorry, 6C minus your released internal reactions released. So for example, if you want to see the total number of internal reactions released, you can take an example of, let's say, an internal hinge. So what we know is that in an internal hinge, the moment about the internal hinge is equal to 0. Exactly. So what it does is that it releases the moment. That's why your number of internal reactions released would be 1 in this case. Okay. So this is all about how to find the degree of static indeterminacy, internal static indeterminacy in case of frames. Okay. So if you want to find the total static indeterminacy, you just have to add the external and internal static indeterminacies. So problems related to this we'll be doing in the next video. So thank you for watching.